back to real time digital signal processing course. So, you can see that we are going to discuss the fourth part of IIR filters today. So, why FIR has not taken so much of time, why IIR is taking, you will be seeing in a while, although we have already seen that quantization how it is going to affect. So, in today's class we will work out and then see how the center frequency is going to move from with the coefficient quantization from one value to the other one. So, as a recap, so we have been seeing the theory of IIR filters and how to design them, and then how the cascade filter section is going to aid us to implement in DSP processor. Just to comment on it, so we know that cascade section is nothing but it is a multiplication. So, in DSP processor we have seen in the number system that when we do multiplication of two numbers, the overflow is not going to happen. Only if we have to do the addition, we have to take care of overflow and then underflow. So, the parallel section is equivalent to addition. So, that is the reason why we will not use parallel structure in case of IIR filter design for these hardware units. So, usually we go with the cascade realization, although both cascade and then parallel section have the same effect on the design. Coming to the thing, so we will see that how we will be seeing what happens, what is our transfer function is going to look like. So, we are going to design a bandpass IIR filter to be used in our digital clock recovery for a 4.8 kilobits per second modem what we are using it, which is characterized by the following transfer function. So, you have been given your impulse response h of z is equal to 1 by 1 plus a1 into z minus 1 plus a2 into z minus 2. So, it should be triggering in your mind that this is just a second order design what we are doing it. So, in this case you have been given the values of a1 and then a2. a1 is given as minus 1.957558 and a2 is given as 0.995813. So, your a1 and a2 can be designed from using MATLAB, or this value has been computed and then you have been given in this equation. So, assuming in this case, because we are using in the clock recovery, sampling frequency of what we are telling is 153.6 kilohertz, to assess the effects of quantizing the coefficients, what we are going to do to 8 bits, that also you have to keep it in mind. So, if you want to increase it to 16 bits, you can do it and then verify what will be the center frequency which is going to remain. That is what one of the assignment what I will be putting it for you. So, then we have to say that how the pole positions is going to affect our this thing center frequency. So, we will do that. So, as we know that we have the equation how to calculate our P1 and then P2 value. So, P1 is my this thing pole position of the first one, which is given r at an angle of theta, and then P2 is given at an angle r at an angle of minus theta, because we are designing the complex conjugate poles in this case. So, we had the equation that r is equal to a to the a2 to the power of half, and then theta is given by your cos inverse minus a1 by 2r. So, in this case how do we compute r? So, we have been given the value of a2, as you can see a2 is given as 0.995813, which we are going to take it as square root of it, because that will give me a2 value. So, we are going to get 0.99795, what I will be getting it here. So, that is r squared is a2. So, r will be square root of a2 what you are going to have. So, theta is going to be cos inverse a1 divided by minus a1 by 2r. So, we know that a1 is negative. So, that is the reason why you will be seeing positive here. This is 1.957558 divided by 2R. To R is going to be whatever what you have computed here. So, we will be putting into that, which gives me in terms of degrees as 11.25 degrees. Fine. So, this corresponds to a center frequency of 4.799 kilohertz. So, what do we mean by that? So, we know that this is my unit circle. So, this is my center. So, we are calculating R here. So, this is R at an angle of what we call it as 11.25 degrees. You have the pole. Okay. This is 11.25 degrees. So, when I calculate center frequency, that what we are going to do is, this is my sampling frequency what it has been given, and I know its degrees 11.25 degrees divided by 360 degree, which is going to give me the center frequency. So, for this it is at 4.799 kilohertz is the center frequency. It is in the original state what we will call it. Now, what you have been given in the problem is, we have to quantize the coefficients to 8 bits. That is what our constraint, as one of the coefficients is greater than unity. So, you will be seeing that A1 is minus 1.957558. So, we need at least 1 bit to represent my coefficient in the integer format. So, what will be the representation here? So, we can in the normal case, we say that it is Q15 format is 1.15 format for 16 bits number. Here you have been given 8 bits basically. So, normally if we allocate all the 7 bits, one is the sign bit and rest of the 7 bits, then I will be talking about 1.75 or 1.7 format. But since my integer value is greater than 1, so I need 1 bit for my integer. So, what happens to this? We will be representing it as 2.6 format. This is the format what I need to represent this value. Then what happens? I have 6 bits for my fractional representation, which I have to convert it. So, my coefficient from A1, it is going to be A1 dash, what I will be putting it, minus 1.957555 into 2 power 6, which is equivalent to, I will be rounding off or truncating one of the thing what you can do it. So, which comes out as minus 1.2 minus 125. So, if you represent in binary, this is the value what you will be representing it. So, coming to A2 dash, so which is given as minus 0.995913. So, into 2 power 6, which comes out as 63. So, it may come out as 63.5 or 63.6, exact value you can check the thing. So, why we are representing this also in 63, I will hold on for a while, we will come to that. This is your binary representation basically, fine. So, now we will go back and then recalculate what are the values we have got it. Okay. So, my maximum value, what is it? 125 for A1, what I have represented in with 8 bits. Then we said that it is 2 power 6 is nothing but 64. So, I can redivide the value and calculate what I am going to get it. So, it becomes 1.953125. So, what was the original this thing? 957558. So, you will be seeing that there is a quantization which has already happened. Even A2 you can see that we are doing 63 by 64, which comes down to 0.984375. So, what was the original one was 0.995913. So, now with this modified, calculate your center frequency, apply the same equations as the previous one. We call that as R dash and theta dash what we will be calculating. So, you are seeing that from 11.54 degrees it has come down to 10.17. If you want to round it off to 2 digits, it is going to be that degree. So, now calculate is your F naught, that is the center frequency. So, this is what you will be getting it, 10.17 divided by 360 into 153.6 into 10 power 3, because it is in kilohertz. So, you can see that this is going to be 4.3399 kilohertz. So, what was our original thing? It was 4.799 kilohertz. So, you will be seeing that your center frequency has moved. What we call it as center frequency in this case is where I am dropping down. This is, we usually call it as my cutoff frequency FC. Okay. So, you will be seeing that your thing from 4.799 it has got moved to 4.3399. So, you will be seeing that your thing has moved to left. So, you are allowing more whatever we call it as in the stop band region. So, that if there are going to be some aliasing, so it may creep into the thing. So, this is the effect of moving quantization basically. So, now I said I can take R is equal to 1. Okay. What happens in that case? So, we recalculate this. So, we have calculated and only we are giving the final thing. So, you will be seeing that what happens to your theta dash, it becomes 12.43 degrees and F naught becomes 5.303 kilohertz actually in this case. Fine. So, what happens? This is FC, this is I call it as FC dash and this I can call it as FC double dash. So, this will be coming to 5.303 kilohertz here if it is represented in kilohertz. Fine. So, my FC double dash. So, you will be seeing that more frequency will be coming into your input and then you will have a problem. Here you are going to reduce the thing if there are any frequency component present in this thing is going to be cut off, whereas here more frequency has come in. So, you will be having the aliasing effect. So, that is the reason why we choose R is equal to 63 in this case. So, which is almost nearer to our 4.799 compared to going beyond the frequency. So, this shows that how your number of bits is going to affect. So, now you can calculate n is equal to 16. So, what is the frequency, how much difference you can get it, you can calculate and then give the result. Okay. Continuing with the thing, how the next one is what is the word length requirement for stability and desired frequency response, what we have to say. So, our stability discussions will be restricted to second order filter sections, because each individually if they are stable then we say the complete IIR filter is stable, since these are the basic building blocks of any filter. And consider our second order section characterized by the familiar equation what you are seeing it here, that is h of z is given by b naught plus b 1 z minus 1 plus b 2 z minus 2, which represents our zeros, divided by 1 plus a 1 z minus 1 plus a 2 into z minus 2. So, a 1 and a 2 are our pole position. So, in the equation what you will be getting is y of n is k is equal to 0 to 2. So, b k into x of n minus k, this is our 0 representation minus our pole position, that is feed, this is the feed forward section and this is the feed backward section. So, we know that poles or the roots of the denominator are located at what we call it as p 1 is equal to half minus a 1 plus a 1 squared minus 4 a 2 to the power of half or square root of a 1 squared minus a 2, and p 2 will be the complex conjugate. So, of p 1 what will be representing it. So, what happens in this case? A digital, we will take up an example. A digital filter required to that is satisfy the following frequency response specifications, determine a suitable transfer function for the filter and then determine a suitable coefficient word length to maintain stability and satisfy the frequency response specification. So, you will be obtain and plot the frequency response of the unquantized filter and those of quantized filters corresponding to this part basically, how you will be number of bits what you will be considering. So, what is the specification what we have? Passband region is given by 20.5 to 23.5 kilohertz and then stop band is given. So, you will be seeing this is a band pass filter basically. So, how it is represented, this is the way I represent it, and then this is given as 20.5 to 23.5 is my passband region, this is in kilohertz I will put it. So, then what are the stop band? So, we will call it as this as FC1 is equal to 19 kilohertz, sorry it is becoming little small, and then here FC2 is going to be equal to 25 to, because it is sampled at 100 kilohertz as you can see, till pi by 2 it is going to be your stop band region in this case 25 to 50 kilohertz. And then ripple what you want is less than or equal to 0.25 dB, and then stop band attenuation what I want is greater than 45 dB. So, as you know that it is better to design this filter using MATLAB and then get the values of your coefficients basically. So, when you do that, this is from the book I have taken the example. So, you can refer to the book and then see CD of the book is going to give you these examples. This is basically from IIR what I have taken the thing real digital signal processing book. So, in this case what happens, it generates as in the lab we will be seeing it that how many sections it is going to create. So, here there are 4 second order sections which has been created, and then using their zeros and then poles you will be representing your impulse response like this H1, H2, H3 and the H4. So, you will be seeing that this is in a cascade form basically. There will be 4 sections what I am going to have. This is my H1 of Z, H2 of Z and then this is H4 of Z. So, these are the values what you will get it. Okay. So, you have to take each second order section and then see whether there is going to be overflow or underflow or what is the number of bits what you needed, so that you are going to have the stable filter. As you can see in this case, so you will be varying your number of bits, that is 2 to 2,3 like that you can keep on changing and then you can go up to 29 bits. So, that is what the theory gives basically. So, we will work out for H1 of Z. So, what is the number of B bits we will assume, because even in the previous example we had taken 8 bits, we will see whether it is going to give us a stable filter. So, you will be seeing that A1 will be, because all the coefficients are less than 1. Now, what I can represent this as a 1.7 format. That is why you will be seeing multiplication by 2 power 7 is happening, and then we are doing the rounding, that is the reason why we are adding 0.5 to that. So, the value is going to be minus 22.8104. After that we will be truncating the value. So, which is going to give us minus 22. Same thing we will calculate A2. So, it will be giving us 124.1736. So, you will be truncating here, which is going to give us 124. So, the fractional notation, the coefficients are nothing but minus 22 divided by 128. So, this is in decimal value. So, when I represent it in fraction, so it will be giving out as minus 0.171875. So, you have seen, I think, something triggering in your mind. So, the coefficient quantization has already happened with 8 bits, 0.1742 0.171 what it has got reduced in this case. So, A2 will be becoming 0.96875. So, original was 0.9662. So, you have seen that it has got, because we have taken a round off, it has got little bit increased compared to the original one. So, with this you can go back and then calculate your r and theta value, and see that what we are going to get is 84.99 degrees what we are getting it. So, what it says is the all quantized coefficients and polar coordinates were computed using an analysis program, and if for any coefficient word length the pole radial distance of a filter section is equal to or greater than unity, then there is potential instability. That is what the literature gives, and then it was found that all the filter sections as few as b is equal to 5 bits are required to maintain R stability. So, in general, if the pole of an unquantized second order section is at radius less than r is equal to r is less than 0.9, so what it says is instability is unlikely. So, if it is greater than or equal to 0.9, you may say that the system may become unstable, then you have to take care of designing the proper stable filter. So, as with the word length 8 bits, we see that it is 0.96875, what we have is 0.9843. So, is more used in this case. Okay. So, to see that B coefficient of second order section were each quantized to various word lengths. So, you have to use your MATLAB code to do these things, and then you can vary your word length 5 to 16 bits, and then how they are going to be represented is given in the table here. This is my poles, that is A coefficients, and this represent zeros, that is B coefficients. For 5 bits, what we want is ideal is this one, and then with 16 bits how almost closer what we are, as you can see that most of the 16 bit is closer to the original one what we say it. So, this is how we will be calculating and then fixing our number of bits. That is the something should be triggering in your mind. All DSP processor, most of them are 16 bit defined, and then we have to this is one of the this thing, quantization of our coefficients, how it is going to vary the thing. Next is we have to take care of overflow errors and their effects. Based on it, what we have to decide on it. So, we know that in 2's complement arithmetic, the addition of two large numbers of a similar sign may produce an overflow. If it is beyond our representation, we are going to have an overflow. So, that it exceeds the permissible word length, and then a very large negative number, if you are adding them negative numbers, you may have a underflow in that. So, these are the two things what you have to look at it. What is that? We will see in the figure what is the thing happened. So, the value is getting added here from here to here, it has gone to the positive value we will assume, and then what happens? So, when my number of bits are not sufficient, immediately it drops down to the negative value, and then again it start building up. Once it reach the peak value, it is going to drop down. So, this is how it will be oscillating between -1 and then 1 if this overflow or underflow is not taken care of. So, what it says is large scale overflow occurs at the outputs of the adders and may be prevented by scaling the inputs to the adders in such a way that outputs are kept low, but this is at the expense of reduced signal to noise ratio, because you are bringing down your amplitude of the signal, then my signal to noise ratio is going to have a effect on it. So, that is how it is important to select scale factors to prevent overflow while at the same time maintaining my largest possible signal to noise ratio. So, coming to the thing, you will be seeing that overflow illustration is shown in this figure. So, you have B0, B1, B2 are the forward coefficients, and then A1 and A2 are the feedback coefficients. So, those both minus A1 and then A2, and what is the scaling factor we will be providing it. One of the section, if I am correct taking it up, it is going to be scaled by 1 by S1 at the input. There are different places where you can do the scaling, whether at the input or at the output, or if you are providing any of these sections, you have to integrate into all the arms basically to take care of that. You have scaled everything fine. So, as you will be seeing using the MATLAB when you are doing it, the scale factor is given in the beginning itself. So, that has to be used and then your filter has to be designed. So, what is the principle of scaling? So, first we will consider the canonic section, because this is the one most widely used in all hardware implementation. That is what we are seeing it. As I said that it is scaled by 1 by S1, and when we want to get back of our yn, either I can scale up here or provide at these legs. Okay. So, if I take the scaling factor inside, as I was mentioning in the original thing, this is going to be B0 by S1 and B1 by S1 and then B2 by S1. When we are loading our coefficients itself, if we want, we can scale them if they are power of 2. If they are not, then you will be having little computation involvement in designing your IIR filter. So, you will be seeing that in the end what you can do is I can scale the output by S1 value. Okay. So, you will be seeing that what are the principles to use the scaling. So, most of you would have heard of what we have norms basically. It can be L1 norm, L2 norm or L infinity are the 3 norms what we have in literature. So, what is that? First we will see the L1 norm, we call it as scaling by as S1. So, here it says k is equal to 0 to infinity. So, I am going to take the frequency response of my input and take the magnitude of it and then calculate the summation of all of them. So, as it says f of k is the impulse response from input to the output of the first adder, that is W of n in our figure here. This is what I will be taking the impulse response of that. And then in the second method, often we usually call it as L2 norm, the scale factor is calculated this way. So, if you want, you can call it as S2 here, or we can have it as S1 is the scaling factor, what notation what we are using it. So, in this case you will take the impulse response, but you will be taking the square root of the value what you have summed value what you have calculated. So, that is what it says. Scale factor may be obtained using contour integration via the relationship. The last one, L infinity norm, what you are going to do is k is equal to 0 to infinity, what I have to calculate f of k impulse response. So, which is given as 1 pi 2 pi j. This is the L2 norm what we are doing with the contour integration, as you can see it, integral of f of z into f z minus 1, this is a complex conjugate what I have taken the thing, dz by z, where your f of z is the z transform of your f of k impulse response, and this is represents our contour integral on around the unit circle, magnitude of z is equal to 1 basically. So, evaluating this is much easier. So, if you want, you can go to the book and then refer to the steps involved in deriving this equation, final equation in terms of your poles, basically what it is calculated. So, you will be calculating the contour integral of your poles in conjugate form dz by z. So, if you do the simplification of it, what the simplest one you will be getting, it is 1 minus a2 squared minus a1 squared into 1 minus a2 divided by 1 plus a2. So, this is how one can manually calculate our L2 norm using this. So, in method 3 we calculate peak amplitude of the frequency response between the input and then W of n. That is, we will be taking the Fourier transform and then the peak amplitude whatever it has it. So, we will be giving that as our scaling factor. So, these are the underlying methods what we have it. So, you can read the theory. Compact way of expressing the scale factor, what we call it as S1 is our L1 norm, what we have it with P. So, you will be seeing that this is represented as norm, and the method what we are going to have it is L1 norm, L2 norm are in L infinity norm, and then how the scaling factors are going to get themselves aligned or compare what we will be seeing it. So, L2 norm is the minimum, and then next comes the L infinity, and then L1 is the maximum what you would have scaled. So, the value of L2 is less than your L infinity, which is less than L1. So, we will take up an example and then see how we are going to calculate this. So, in the book it says that the figure whatever in 13.19 is being used, and then we have this is our second order section for the example. Then what is the thing is going to happen. So, either using flow diagram, what you can flow analysis you can use the thing, or you can use the book if you are using the thing CD, which is the companion which is going to have it. So, you will be getting these codes for this program and then you can run it. So, you can evaluate all the equations in your book and then get the scale factors for 3 methods which it is computed, and then you will be seeing it. So, for the L1 norm it is 3.7112, and for L2 norm it is 1.7352, and then L infinity 3.5863 what you will be getting it. So, one of the thing what we can compute, we know that we have the equation to calculate our L2 norm. So, which is given as S1 squared is equal to 1 by this your A1 and then A2 what you will be substituting and calculate. So, when you calculate it, S1 is coming as 1.7350. So, which is closer to whatever the software has calculated the thing. So, this is how you can do that. So, the thing is given as your B0, B1, B2, and then this is the diagram what you have it for the example there, and then go and then look at them. So, if you are realizing the scaling factor for cascade realization, so you will be seeing that each one has to be calculated, and then how you will be rescaling back in the in between what you can see it. One of the norms what you can use that. Fine. So, this is how you will be selecting it. So, one of the ways either you can have the division done when you are storing your after multiplication before summation, you can scale them and then do the addition. That way you will be avoiding your overflow instead of adding them, and if there is a overflow and then dividing it later. So, you can provide the scaling factor at this itself. So, this shows for the 6th order IIR filter how you will be doing the scaling part of it, and then the final one you will be multiplying only by S3 whatever scaling you have done. So, you will be accounting for S3 and then you will be sending the output y of n. So, this is what the S2 and S3 for the figures you can compute. So, these are the cascade section H1, H2, H3 using MATLAB. You can calculate them and then you can get the thing. So, if you use your FWS program, so the solution you will be seeing that L1, L2, L infinity for the 3 sections what it is calculated. As given in the thing, L2 is going to give you the minimum this thing scaling factor, and then the maximum is L1, L infinity lies in between. The simplest method to calculate is L2. So, if your application is going to overflow and then you are going to get results malfunctioning, then better to go with one of these norms L1 or L infinity, which is going to suit your application. So, just the last slide to wind up our IIR filter. So, we will be seeing the comparison between our FIR and IIR filter. Few of the parameters what you can see the thing, 1 or 2 I will specify and rest of it you can go through. So, that is sensitivity to filter coefficient quantization. So, it can be as high, it says in Motorola they use the 24 bit coefficients to for high fidelity audio function in their processor. Otherwise, all TI or analog devices they use 16 bit for their number representation. So, in the case of we know that FIR filter it is very low and it says 16 bit coefficients are safely represented or computed using that. And then probability or overflow it can be very high in this case, which is going to be very low, and coming with our linear phase we do not have IIR filter direct method to implement it, but nowadays over the IIR filter you can try to impose the linear phase. So, using software techniques, so you can go through the MATLAB functions. So, otherwise they do not provide the linearity of the phase, whereas it is guaranteed, and rest of the thing what you will be seeing it. One of the example will be supporting supports adaptive filtering what it says. So, both of them support adaptive filter. So, we will be considering it in the next after a few classes later. So, coming to the end of it, which finishes our filter design. So, we will be taking our DFT and then FFT in the next class. So, thank you for listening to this lecture and then happy learning through this media. Thank you.